Working with mnemonic codes. BIP39 is implemented as a library in many different programming languages. For example, 1. Python-mnemonic, the reference implementation of standard by the Satoshi Lab team that proposed BIP39 in Python. 2. Consensus/ETH-Light Wallet, lightweight JS Ethereum wallets for nodes and browser with BIP39. 3. npm/BIP39, JavaScript implementation of Bitcoin BIP39, mnemonic code for generating deterministic keys. There is also a BIP39 generator implemented in a standalone web page, which is extremely useful for testing and experimentation. The mnemonic code converter generates mnemonics, seeds, and extended private keys. It can be used offline in a browser or accessed online. Creating an HD wallet from the seed. HD wallets are created from a single root seed, which is a 128, 256, or 512-bit random number. Most commonly, this seed is generated from a mnemonic as detailed in the previous section. Every key in the HD wallet is deterministically derived from this root seed, which makes it possible to recreate the entire HD wallet from that seed in any compatible HD wallet. This makes it easy to export, backup, restore, and import HD wallets containing thousands or even millions of keys by transferring just the mnemonic from which the root seed is derived. HD wallets, BIP32, and paths, BIP43-44. Most HD wallets follow the BIP32 standard, which has become a de facto industry standard for deterministic key generation. We won't be discussing all the details of BIP32 here, only the components necessary to understand how it is used in wallets. The main important aspect is the tree-like hierarchical relationship that it is possible for the derived keys to have, as mentioned in the previous section. It's also important to understand the ideas of extended keys and hardened keys, which are explained in the following sections. There are dozens of interoperable implementations of BIP32 offered in many software libraries. These are mostly designed for Bitcoin wallets, which implement addresses in a different way. They share the same key derivation implementation as Ethereum's BIP32 compatible wallets. Use one designed for Ethereum or adapt one from Bitcoin by adding an Ethereum address encoding library. There is also a BIP32 generator implemented as a standalone web page that is very useful for testing and experimentation with BIP32. Warning: the standalone BIP32 generator is not an HTTPS site. That's to remind you that the use of this tool is not secure. It is only for testing. You should not use the keys produced by this site with real funds. Extended public and private keys. In BIP32 terminology, keys can be extended. With the right mathematical operations, these extended parent keys can be used to derive child keys, thus producing the hierarchy of keys and addresses described earlier. A parent's key doesn't have to be at the top of the tree. It can be picked out from anywhere in the tree hierarchy. Extending a key involves taking the key itself and appending a special chain code to it. A chain code is a 256-bit binary string that is mixed with each key to produce child keys. If the key is a private key, it becomes an extended private key distinguished by the prefix XPRV. For example, XPRV9S ... An extended public key is distinguished by the prefix XPUB. For example, XPUB661MY ... A very useful characteristic of HD Wallet is the ability to derive child public keys from parent public keys without having the private keys. This gives us two ways to derive a child public key, either directly from the child private key or from the parent public key. An extended public key can be used, therefore, to derive all of the public keys and only the public keys in that branch of the HD wallet structure. This shortcut can be used to create very secure public key-only deployments. where a server or application has a copy of an extended public key, but no private keys whatsoever. That kind of deployment can produce an infinite number of public keys and Ethereum addresses, but cannot spend any of the money sent to those addresses. Meanwhile, on another, more secure server, the extended private key can derive all the corresponding private keys to sign transactions and spend the money. One common application of this method is to install an extended public key on a web server that serves an e-commerce application. The web server can use the public key derivation function to create a new Ethereum address for every transaction, for example for a customer shopping cart, and will not have any private keys that would be vulnerable to theft. Without HD wallets, the only way to do this is to generate thousands of Ethereum addresses on a separate secure server, and then preload them on the e-commerce server. That approach is cumbersome and requires constant maintenance to ensure that the server doesn't run out of keys. Hence the preference to use extended public keys from HD wallets. Another common application of this solution is for cold storage or hardware wallets. In that scenario, the extended private key can be stored in a hardware wallet, while the extended public key can be kept online. The user can create receive addresses at will, while the private keys are safely stored offline. To spend the funds, the user can use the extended private key in an offline signing Ethereum client, or sign transactions on the hardware wallet device. Hardened child key derivation. The ability to derive a branch of public keys from an extended public key or XPub is very useful, but it comes with a potential risk. Access to an XPub does not give access to child private keys. However, because the XPub contains the chain code used to derive child public keys from the parent public key, if a child private key is known or somehow leaked, it can be used with the chain code to derive all the other child private keys. A single leaked child private key together with a parent chain code reveals all the private keys of all the children. Worse, the child private key together with a parent chain code can be used to deduce the parent private key. To counter this risk, HD wallets use an alternative derivation function called hardened derivation, which breaks the relationship between parent's public key and child chain code. The hardened derivation function uses the parent's private key to derive the child chain code instead of the parent public key. This creates a firewall in the parent/child sequence with a chain code that cannot be used to compromise a parent or sibling private key. In simple terms, if you want to use the convenience of an XPub to derive branches of public keys without exposing yourself to the risk of a leaked chain code, you should derive it from a hardened parent rather than a normal parent. Best practice is to have the level 1 children of the master keys always derived by hardened derivation to prevent compromise of the master keys. Index numbers for normal and hardened derivation. It is clearly desirable to be able to derive more than one child key from a given parent's key. To manage this, an index number is used. Each index number, when combined with a parent's key using the special child derivation function, gives a different child key. The index number used in the BIP32 parents-to-child derivation function is a 32-bit integer. To easily distinguish between keys derived through the normal derivation function versus keys derived through hardened derivation, this index number is split into two ranges. Index numbers between 0 and 2 to the 31st minus 1 are used only for normal derivation. Index numbers between 2 to the 31st and 2 to the 32nd minus 1 are used only for hardened derivation. Therefore, if the index number is less than 2 to the 31st power, the child is normal, whereas if the index number is equal to or above 2 to the 31st power, the child is hardened. To make the index numbers easier to read and display, the index numbers for hardened children are displayed starting from 0, but with a prime symbol. The first normal child key is therefore displayed as 0, whereas the first hardened child, with index 0x8000000 is displayed as 0 prime. In sequence, then, the second hardened key would have index of 0x8000001 and would be displayed as 1 prime, and so on. When you see an HD wallet index I prime, that means 2 to the 31st power plus I. HD wallet's key identifier path. Keys in an HD wallet are identified using a path naming convention, with each level of the tree separated by a slash character. Private keys derived from the master private key start with small m. Public keys derived from the master public key start with big M. Therefore, the first child private key of the master private key is small m/0. The first child public key is big M/0. The second grandchild of the first child is small m/0/1, and so on. The ancestry of a key is read from right to left until you reach the master key from which it was derived. For example, identifier small m/x/y/z describes the key that is the cth child of the key small m/x/y, which is the yth child of key small m/x, which is the xth child of m. Navigating the HD wallet's tree structure. The HD wallet's tree structure is tremendously flexible. The flip side of this is that it also allows for unbounded complexity. Each parent's extended key can have 4 billion children, 2 billion normal children, and 2 billion hardened children. Each of those children can have another 4 billion children, and so on. The tree can be as steep as you want, with a potentially infinite number of generations. With all that potential, it can become quite difficult to navigate these very large trees. Two BIPs offer a way to manage this potential complexity by creating standards for the structure of HD wallet trees. BIP 43 proposes the use of the first hardened child index as a special identifier that signifies the purpose of the tree structure. Based on BIP 43, an HD wallet should use only one level 1 branch of the tree, with the index number defining the purpose of the wallet by identifying the structure and namespace of the rest of the tree. More specifically, an HD wallet using only branch m/i'/ is intended to signify a specific purpose, and that purpose is identified by index number I. Extending the specification, BIP 44 proposes a multi-currency, multi-account structure signified by setting the purpose number to 44 prime. All HD wallets following the BIP 44 structure are identified by the fact that they only use one branch of the tree, small m/44 prime/star. BIP 44 specifies the structure as consisting of 5 predefined tree levels, small m/purpose prime/coin type prime/account prime/change/address index. The first level, purpose prime, is always set to 44 prime. The second level, coin type prime, specifies the type of cryptocurrency coin, allowing for multi-currency HD wallets where each currency has its own subtree under the second level. There are several currencies defined in a standard document called SLIP 0044. For example, Ethereum is m/44 prime/60 prime. Ethereum Classic is m/44 prime/61 prime. Bitcoin is m/44 prime 0 prime. And testnet for all currencies is m/44 prime/1 prime. The third level of the tree is account prime, which allows users to subdivide their wallets into separate logical sub-accounts for accounting or organizational purposes. For example, an HD wallet might contain 2 Ethereum accounts, m/44 prime/60 prime 0 prime and m/44 prime /60 prime /1 prime. Each account is the root of its own subtree. Because BIP44 was created originally for Bitcoin, it contains a quirk that isn't relevant in the Ethereum world. On the fourth level of the path, change, an HD wallet has two subtrees, one for creating and receiving addresses and one for creating change addresses. Only the receive path is used in Ethereum, as there is no necessity for a change address like there is in Bitcoin. Note that whereas the previous levels used hardened derivation, this level uses normal derivation. This is to allow the account level of the tree to export extended public keys for use in a non-secure environment. Usable addresses are derived by the HD wallet as children of the fourth level, making the fifth level of the tree the address index. For example, the third receiving address for Ethereum payments in the primary account would be big M/44 prime /60 prime /0 prime /0/2. The following table shows a few more examples. Big M/44 prime /60 prime /0 prime /0/2 is the third receiving public key for the primary Ethereum account. Big M/44 prime /0 prime /3 prime /1/14 is the 15th change address public key for the fourth Bitcoin account. Small m/44 prime /2 prime /0 prime /0/1 is the second private key in the Litecoin main account for signing transactions. Conclusions. Wallets are the foundation of any user-facing blockchain application. They allow users to manage collections of keys and addresses. Wallets also allow users to demonstrate their ownership of Ether and authorize transactions by applying digital signatures, as we'll see in the transactions chapter.